Hello everyone. Let us discuss about the topic Mathematical Modeling of Electrical Systems under Unit 1 of Control Systems. The objective of this video lecture is to introduce the components and their representation of the electrical systems and analogous systems. First, elements of electrical systems are having three elements. Similarly, for mechanical rotation system and as well as mechanical translation system, here the resistance is the one of the first element and inductors and then capacitor. So this is a resistance. When the resistance is having current flowing through the resistor, so how to write the equation for this one is, so V of t is equal to I of t into R. So for Laplace transform for this equation is V of s into I of s into R. Similarly for inductance, so current flowing through the inductor is V of t is equal to L into di of t by dt. So differentiation means only numerator you put S. So that L into S into I of s for Laplace transform. Similarly for capacitance, so current flowing through the capacitor is V of t is equal to 1 by C integral of I of t into dt. So for integration, you get the Laplace transform here is V of s is equal to I of s 1 by Cs. For integration, 1 by S you put. Next, this table represents the current voltage relationship of RLC element in an electrical circuit. So first element is resistors. So for current flowing through the element is I of t. So I of t is equal to V of t by R. So voltage across the element V of t is equal to R into I of t. Next one, the inductor. So the V of t, there is a voltage across the element V of t is equal to L into di of t by dt. Whereas in the case of current flowing through the element is I of t is equal to 1 by L integral of V of t into dt. The next one is the capacitor. The current flowing through the element is I of t is equal to C into dVt by dt. So whereas voltage across the element is V of t is equal to 1 by C integral of I of t into dt. Next, the problems related for electrical system. So this is a given problem. There is a given circuit. So in this circuit, you can find the transfer function for this given electrical circuit. Here the R and the C's are in series. Okay. The capacitor having the impedance C and resistance having the impedance R. So here having the input voltage Vi of t and output voltage V naught of t. So now you can apply the KVL for this input side in this loop. So Vi of t is equal to, that is what is the KVL you know already. So algebraic sum of all the applied forces equal to algebraic sum of all the opposing forces. So Vi of t is equal to R into I of t plus 1 by C integral I of t into dt. So next you can write the output equation also. So V naught of t is equal to R into I of t, because the voltage drop across resistor is nothing but your output voltage. So now we take the Laplace transform for this equation 1. So we can get Vi of s is equal to R I of s plus 1 by Cs into I of s. You take the common factor for this one, I of s, and rewrite this equation. Vi of s is equal to R plus 1 by Cs into I of s. So next to take the Laplace transform of this equation. So V naught of s is equal to R into I of s. So rearranging this one. So V naught of s by R is equal to I of s. Substitute this R, I of s into this equation. So we can now Vi of s is equal to R plus 1 by Cs into V naught of S by R. but your transfer function is nothing but the ratio of Laplace of input to Laplace of output. So V naught of S is the output for this network and Vi of S is the input voltage of the electrical network. So that V naught of S by Vi of S is equal to RCS divided by RCS plus 1. So this is a transfer function for the given problem. So next, another example, there is RLC series circuit. Okay, so RLC series circuit means the R, L and the C's are connected in series. Okay, so applying the Kirchhoff voltage law, so sum of voltage is equal to 0. So that EI of T is the input voltage here, E naught of T is the output voltage. So that EI of T is equal to EI of T minus, this is applied force. Okay, so algebraic sum of voltage is equal to 0. So EI of T is minus L into di of T by dt. Because why putting minus means these are all the opposing voltages. Okay, so L into di of T by dt. So R into I of T minus 1 by C integral of I of T into dt is equal to 0. Name it as the equation number 1. So from this equation, what is the output equation from this circuit? What is the output equation? So 1 by, that is the output equation means here the voltage drop across the capacitor is nothing but output voltage. So that E naught of S, E naught of T is equal to 1 by C integral of I of T into dt. So now taking the Laplace transform for this first equation. So EI of S is equal to LSIS plus RIS plus 1 by CS into IS. So next, take the Laplace transform for this equation. So 1 by CS I of S into is equal to E naught of S. So now you write the equation in terms of electric charge. Q is equal to integral of I into dt. Okay, Q is equal to integral of I into dt. So that you can write the equation L into d square Q by dt square plus R into dq by dt plus 1 by C into Q is equal to E into I. Okay. So next, similarly for RLC parallel circuit. So in previous case, RLC are in series. Now the RLC are in parallel. So here having the current flowing through this one is I and output is voltage. So applying the Kirchhoff current law. So what is the Kirchhoff current law means? So the algebraic sum of current meeting at a junction is 0. So that C into dE by dt, C into dE by dt plus 1 by L into E into dt plus E by R is equal to I. This is the equation number 3. So in terms of magnetic flux, you can write pi is equal to E into dt. So change this equation in terms of flux, magnetic flux. So C into d square phi by dt square plus 1 by R into d phi by dt plus 1 by L into phi is equal to I. Name it as equation number 4. You know already for the mechanical translation system having one mass, dashpot and spring. So having applied forces there, you can write like this. So m into d square x of t by dt square plus b into dx of t by dt square plus kx is equal to f of t. Name it as the equation number 5. Similarly for mechanical rotation system, you write the equation. So j into d square theta by dt square plus b into d square by d theta by dt plus k theta is equal to t of t. Name it as the equation number 6. So next, that is analogous systems. What is analogous system means? Electrical and mechanical systems, there exist a fixed analog and there exist similarities between their equilibrium equations. So the possible to draw an electrical system which behave exactly similar to mechanical system, this is called electrical analogous of the given mechanical system and vice versa. If the analogous electrical system is visualized for a given mechanical system, it is easy to redact the behavior of the system using the well-developed mathematical tool of electrical system. So designing and constructing a model easier in electrical system. The system can be built up with check elements. The values of the elements can be changed with is an experimentation of easy with electrical circuits. So there are two methods of obtaining the electrical analogous networks, namely force voltage analogs that is in the direct analogs. So next one is a force current analog, that is inverse analog. So next, so how does this? This table shows the force voltage analog. That means is a direct analog. So the previous slides, I am deriving that what is the RLC and RLC series and RLC parallel circuit equations. So for this equation 2, L into d square q by dt square plus R into dq by dt plus 1 by cq is equal to EI. Okay. Similarly for this, you can compare these three equations 2, 5 and 6. So compare these three equations. Now you can look at the table. So for force F, that is a translation system here. This is the rotation. This is the electrical. Okay. This is the force voltage analog. So that force here you can compare these three equations. So F of t is the applied torque here. Sorry, applied force. And similarly for rotational torque. So that inductance is E. In electrical system, there is a voltage E. So next one is a mass. Mass is presented here, equivalent to moment of inertia J. And here is what is the element for this one is inductance L. Next one is a damper B. So here also B. But in this electrical system, the resistance will be there. You put resistance. Next one is a spring element K. So that here also K. So in this electrical equation 1 by C. It is reciprocal of resistor. So for the displacement for translation system is X and rotation system is theta, and this one is for charge in terms of charge. So this is a velocity in terms of V. Here the velocity is angular velocity. So this is the current flow through this one. Similarly, next in this table, so force current analog, that is inverse analog. You can compare these three equations. That means 4, 5, 6. You can compare these three equations. So that the first you know already force F and torque T, the corresponding current I. Okay, for electrical system. So that next M, here J, here C. Instead of L, here C capacitance. So next B, here also B, here 1 by R. That is a reciprocal of resistance, that is a conductance. So next one is a spring K, here also K. So that in the electrical system reciprocal of inductance 1 by L. So here the displacement x, the displacement theta, and the flux linkage phi. So for the velocity for transition system is v, and rotation system is omega, and electrical system is voltage. So next, the problem for analogous systems. Write the differential equation governing the mechanical system shown in figure. Draw the force voltage and force current electrical analogous circuits and verify by writing the mesh and node equations. So this is the given problem. So in this problem, mass M1 and M2s are presented here. So mass M1 is connected with B1, B12, K1 and having some applied force F of t. And similarly for M2 is connected with again connected with K1 and B12 and K2 B1. So K2 B1's another end is connected with fixed point. So different mass means having different displacement will be presented. So the M1 corresponding displacement is x1 and the M2 corresponding displacement is x2. So now you can draw the free body diagram. So for mass M1, so here the M1 mass having some applied force F of t, the opposing forces due to mass M1, B1, B12 and K1. So these are all the opposing forces are presented. So write the mathematical modeling. So you can apply the Newton's second law. So the sum of the applied force is equal to sum of the opposing forces. Here the applied force is only 1, F of t, and opposing forces having 4. We can add algebraic sum. So Fm1 plus V1 plus B12 plus Fk1. So the corresponding equation for mass is m1 into d square x1 by dt square plus b1 into dx1 by dt plus b12 is in between m1 and m2. So both the displacement will acting on it. So that how it is write the equation. So d of x1 minus x2. So you can consider this point. Okay. So you can now the displacement is x1 minus x2 divided by dt plus similarly for k1 is k1 into x1 minus x2 is equal to f of t. We name it as the equation number 1. So next the free body diagram for mass m2. So this is the free body diagram for mass m2. So in this diagram here only opposing forces are presented. So due to mass m2, k2, spring k2 and spring k1 and dashpot b2 and then b12. Okay, we just added these 5 forces, which is equivalent to applied force 0. So that Fm2 plus Fb2 plus Fb12 plus Fk1 plus Fk2 is equal to 0. So according to the equation, m2 into d square x2 by dt square plus b2 dx2 by dt plus b12 into d by dt of x2 minus x1 plus k1 into x2 minus x1 is equal to 0. You may name it as equation number 2. So in an equation, so you can substitute this d square x by dt square is equal to dv by dt, dx by dt is equal to v, and x is integral of v into dt, because replacing the displacement by in terms of velocity in the differential equation 1 and 2. in the mechanical transmission system. So that M1 into dV1, the equation 1 becomes M1 into dV1 by dt plus B1 V1 plus B12 into V1 minus V2 plus K1 into integral of V1 minus V2 into dt is equal to f of t. This is named as the equation number 3. Next, the second equation becomes M2 into dV2 by dt plus B2 V2 plus B12 into V2 minus V1 plus K1 into V2 minus V1 into dt is equal to 0. We named as this equation number 4. So next, for force voltage analogous circuits, the system has two masses, hence two forces, that is two force voltage analogous electrical circuits which have two meshes, so that here they are having two meshes presented. The next one is that the force applied to mass M1 represents by a voltage source f of t, that is in a first mesh. So here I am applying the input voltage E of t in the first mesh. The elements M1, B1, B12, K1 and K1 are connected to the first node. Hence, they are represented by analogous element in mesh 1 forming a closed path. So that corresponding element M1, K1, B12, B1. M1 is L1. You can refer the table. M1 is L1 and B1 is R1, B12 is R12, K1 is 1 by C1. So here the M1 is L1. Okay, L1. B1 is R1. Okay, both these two are in common between these two nodes, that is M1 and M2 mass. So that common between these two nodes also. You are writing the element K1, B12, K2, B2s are connected in second nodes. So corresponding M2 is L2, B12 is again R12, K1 is 1 by C1, K2 is 1 by C2, B2 is R2. Okay, so the elements K1 and B12s are common between node 1 and node 2, and so they are represented by analogous element as common elements between the two mesh. Okay, so this is a our force voltage analogous circuit. So now we can apply the KVL for the loop 1. So the equation becomes like this. So what is this? L1 into di of t by dt plus R1 into I of t plus R12 into I1 minus I2 plus 1 by C1 integral of I1 minus I2 into dt is equal to applied voltage E of t. Name it as equation number 5. So next, this is that is in the loop, you applying the loop 2. You can apply the KVL at loop 2 for L2 into di of 2 by dt plus R2 into R1 into R2 into I2 plus R12 into I2 minus I1 plus 1 by C1 integral of I2 minus I1 into dt plus 1 by C2 into integral of I2 into dt is equal to 0. We name it as the equation number 6. Next, force current analogous circuit. So here the force current analogous circuit is, the system has again two nodes, hence the force current analogous electrical circuit will have two nodes. Okay, so the force applied to mass M1 is represented as a current source. M1 is represented as a current source to node 1 in analogous electrical circuit. So the element M1, B1, B12, K1 and K1s are connected to the first node. They are represented, this is the node 1, this is node 2. So B12 and L1, there is B12 and L1s are, there is a equivalent element for K1 and B12. These two are common between node 1 and 2. So next the element K1, B1, M1, B12, K2 and M2 are connected to the second node. Hence they are represented by analogous elements as element connected to node 2 in analogous circuit, electrical circuit. So this is where electric force voltage, force current analogous circuits. So this is the equation for applying the KCL. Applying the KCL for this equation. So the V1 is equal, that is C1 into dV1 by dt plus V1 by R1 plus V1 minus V2 by R12 plus 1 by L1 integral of V1 minus V2 into dt is equal to applied current I of t. So name it as equation number 7. So next equation 8 is nothing but the KCL at node 2. Applying the KCL at node 2. So C2 into dV2 by dt plus C2 into dV2 by dt plus 1 by V2 by R2 plus 1 by R12 into V2 by, V2 minus V1 plus 1 by L1 integral of V2 minus V1 into dt plus 1 by L2 into V2 into dt is equal to 0. Hence the node basis equations 7 and 8 are similar to the differential equation 3 and 4 governing the mechanical systems. This one 3 and 4 means this first 3 and 4, these two equations. Similarly, you can compare 5 and 6 also. These are the references I referred for preparing this video lecture. Thank you for watching this video.